chapter or two. So I work for solidThinking, which is a division of Altair Engineering. And Altair, you probably hopefully have heard of, is an engineering company, first and foremost, and a software company. And we've seen a lot about generative design, and I've been seeing topology optimization and a lot of the presentations today. Well, Altair actually was really the first commercial company to put out topology optimization. It goes back 25 years when we introduced OptiStruct back in the early 90s. And we've been applying it in industries for all that time. And solidThinking was an effort by us to actually take some of that type of really cool engineering technology that was put in the hands of the really high-end CAE guys that were doing really sophisticated engineering and put it in the hands of designers and non-CAE specialist engineers. So I'm going to start off with just a quick video. I got to find a clicker here. I guess this must be it. And just kind of walk through a quick process here. And in some ways, this is going to be less of a lesson about what topology optimization is, and maybe a little bit of a warning to some too, because we've been using it for so long, we've learned a lot about it. And I want to just kind of walk you through here. So let's see if this is the right switch. Yeah. Okay, so here's just an example in an airplane wing. So a lot of people just start with doing bracketry, right? So we have an actuator that moves the flaps, very important part, and that red part right there is just a simple bracket. And what we're seeing in the aerospace industry, where we've been practicing, again, for most of that 25 years, we are the actual company that Airbus comes to do optimization on their products. So we've set up optimization centers at Boeing and Airbus and so forth and use this stuff every day. So let's walk through what goes on here. So we're going to redesign that part. It's kind of taken out of the big wing. It's put into just a local area, and we're going to do a quick design study on it. So there was the existing part. And the first thing you have to do is run a benchmark on, or just a baseline on this. So you put your loads on it. We're going to get back to how you get your loads in a minute. You can see it's French, came out of the French office in Altair. And they're doing a quick rundown of all the simulation types that they need, some buckling, some static load cases, and look at the deflections, which are exaggerated so that you can see them. And then the redesign process is really sort of about undesigning. So there's tools in the product here that actually let you quickly convert an existing part into a design space. Now that we have a design space, which is really the packaging space for that entire part, now the optimizer can go to work. We can even put some different scenarios together with this. And that's what really topology optimization, by the way, is about: generating concepts, not final parts. That's a key message I want to get across. So we're playing with different bolt attachments, different manufacturing constraints. We run different scenarios for topology optimization. Once you have the topology results, then you do a process which is an interpretive process. And you can use different methods to do this. Some people want to just print the part as it comes out of topology optimization. Don't do that. That's really dangerous because you have to do a lot of interpretation and additional optimization on this part. They call it topology optimization because all it gives you is topology, not a finished part. So we've come up with a topology that we like. We've created a CAD interpretation of it. We just rerun the simulations that we did to make sure it checks out. And in this case, it was going to be for an additive manufacturing process. And of course, you always get great weight reduction and all that kind of stuff. So really great technology. So that's the basic rundown of how you basically do topology optimization, substitute in the new part, and everybody's super happy, and the plane's going to fly much better now. So a little bit more about topology optimization specifically. So in case you haven't seen it before, probably most of you have, it really comes down to getting the boundary conditions correct on your part. So you put the boundary conditions, you never put them on the design space itself. You need to put them on the surrounding material. So we always have these interface locations where you put the boundary conditions and loads. You do your interpretation. And so just walking through a very simple case, again, here we have just a gripper of a robot arm. You go through that process of removing the details out of an existing design, or you can just start with the design space that you create in your favorite CAD system or in our products. They're typically quite blocky. You run your load cases, you get a number of different results. Again, I want to go back to it generates what you would consider sort of an ideal concept, but not a finished part. You get the topologies out of it, so you know where the load paths are. But how do you know what the actual sizing of those members needs to be? Are they at the exact angles? Topology optimization is not a precise form of optimization. Nobody knows it better than Altair. It is an approximate form of it. It gives you good starting points for your topology, your load paths, but there's still plenty of work to do after that point. If you take away nothing from this presentation but that, then I'll feel that we've had a success here. The other thing is it's highly iterative, right? So you might have different manufacturing processes in mind. In the early concept stages, you may say, well, maybe I'll cast it, and so I'm going to put a casting constraint on this. The manufacturing constraints are a key point in doing topology optimization. So if you're going to do a casting, you have to separate the die, you have draft angle concerns, or maybe you're going to do an additive manufacturing process where you don't have to worry about separating dies. Maybe you need to partition this into separate regions, and each one of them has a separate die direction to it. So there's quite a lot to set up these models to get it for your intended manufacturing purpose. So then once we get the answer from the topology optimization, again, we go ahead and we put on. In this case, I'm going to talk a little bit about these polynurbs that we have. So this is a technology that is sort of similar to what you see in the subdivision surface modeling that's kind of come into vogue now. It's a little different in our case, because what we're doing is actually not creating sub-D surfaces, but we're using that same cage-like approach, and we're generating a network of Nurbs surfaces, properly formed Nurbs surfaces that we call polynurbs. And that's a very important technology for us, because this is where we then begin to do additional work on this design. So we have that same cage-like structure, and you can see it's actually doing a wrap. It's like actually detecting the STL that's underneath there, doing fits around it. We have a number of tools. This is a little old now. But in addition to this kind of interactive approach, you can now start to automatically detect the members in the structure. We're fitting cages around these things automatically. Our hope is to eventually get to just a few clicks to generate a really well-formed cage out of these things. So you'll see this now, and we were seeing in a lot of the earlier presentations, that style, that very organic form of design is really starting to sweep through all of the design language today, especially for structural components. And it's even creating a certain design kind of aesthetic nowadays. But now to the key part. So getting the boundary conditions right. So we've been putting this in the hands of designers, I would say, for the last 10 years with the Inspire product. And what we found over and over and over again is they almost always get the boundary conditions wrong. They leave out load cases. They don't understand how to do constraints properly. They maybe have done some simulation in the CAD system and they've tried, and maybe the results make sense or they don't. They usually get overridden by the CA guys later anyway. But when they're forming the parts using topology optimization, if you get those wrong, it's even worse, because you may fall into some very narrow, non-robust design solution from that topology. And if you miss load cases, you may actually be under-designing your part. So we've been spending the years baking that kind of knowledge into the product so that people don't get into so much trouble. One of the really great ways to avoid the boundary condition trap is to model more of the system. They always want to put the boundary conditions on a single part. That's the hardest thing there is to do. Turns out if you know the rest of the system around your model, you're going to be in way better shape to generate the boundary conditions that go into it. So you can do things like motion simulation. So we put a motion simulation software into our Inspire product to actually help you generate the loads. So the way that works is it takes the loads from the dynamic simulations and it turns those automatically into boundary conditions on those parts that you're doing the design for. So instead of having to go to that link that's in the middle there and figure out, well, what's it doing at all these different stages? You know, there's 5 different load cases where it comes up and down. So it's a moving thing. It's really complicated. That's a lot of load cases. So we just run the dynamic simulation on it, put all the loads in for you. We sort through them. That's not trivial, by the way, because there's quite a lot of sorting to do. Where do you have peaks, and where do they superpose peaks, and where do you have areas you don't need to? You could generate a lot more load cases than you actually need. So there's an algorithm that we've developed over the years that helps sort those out. So now you don't have to worry about how you constrain this thing, and you just got to get the motions right. The other thing you can do with the motion software is use it to construct things like design spaces, for instance. So we have these motions and actuators and springs and dampers and tracers and stuff now that we put in the software this past year. Lets you build a full mechanisms model out of your CAD data and then put traces on it and use those traces to create new geometries and things. So here we're just creating it's a CAM design process right here. We're just going to Boolean that thing out and get a cam. That might become now the design space for this cam that will then get the loads from the motion also and generate what maybe the spokes in that cam ought to be. So having a really good dynamic simulation for motion is a really big part of doing topology optimization correctly for anything that moves. And to do that well, you often have to get contacts, right? Not everything's just a motor and a joint. There's things that bang together. We all know that dynamic loading can be 3-4 times the actual static load of that same thing when you just drop something from, like, say, an inch. So dynamic loading is really, really important in understanding the complex interactions between all the members inside of these functions. So we put quite a lot of effort into getting that right. And then to define all the motion properties. If you're going to do that, you're going to have actuators, you're going to have controllers in here. We have a lot of control system generation software that we use too. But in this case, we can just bring in the motor profiles, actuator profiles. We can let you design those on the fly, get those correct, and iterate that way. And while it's doing that, you'll get all your mechanisms right, then transfer the loads over. So it's important to have good high fidelity motion simulation as part of that. The other thing that we found over the years, and this came out of work with virtually every company that's like Airbus or General Motors or all the auto companies and so forth, is it works best when the designers and the CE people are really working together. And so quite often, they'll have a designer put together some part in the context of a bigger structure. And those structures are often the form of validated CAE models, Nastran models, Abacus models, and so forth. So a big part of getting this right, too, is to be able to import what is known, validated, analyzed structure, bring that structure in with its boundary conditions, weld those in together, bolt them together, whatever the interface is, let the designer then get all his loads from the surrounding structure. That has the added benefit of making the analysts and the designers really work together, which is great. So it's very important that the products be able to really have that kind of mixed mode. It's really a hybrid of designers and CAE people working in this space together. Okay, a few words about interpreting the results that come out of topology optimization. So there's a number of tools that we've been working on to just make that easier. I want to get it down to one click if we can get to there, but we're getting there in stages. So you can kind of click along and you can create your topology using this cage like that as well. We've also got some optimization algorithms in that cage fitting. So you can do a very coarse approximate structure around that cage, and then we'll auto fit it using least squares type approach to make sure that all the paths through that topology skin are as close as possible. Now, a couple of words about the polynurbs that we're creating there. So I said it was closely related to the subdivision surfaces. So it has the same cage-like structure, same approach to creating them, but in the end we create well-formed Nurb surfaces so you can export those into your CAD system rather than STL. That's a big, big deal. The STL can be very fine, weighs a lot, there's a much lighter weight structure. Has the other benefit is that you can do a lot more redesign with this and further optimization, and you can realize it in different ways. So here's a case where we're going to do further shape optimization on this cage. So I can take one of the faces in that cage and I can move them back and forth. I could take vertices and I can stretch them back and forth and say that's a shape variable. And then I can let Inspire rerun additional fine-tuned optimizations on that cage. And it's going to change the underlying structure which that cage now controls. So we've sort of thrown away that original topology mesh that was under there, and now we have a really nice geometry model that has the integrated solver, which is going to modify it and remesh it as it needs to in those local areas. So you can use it to fine-tune your structure, get stresses out where there's little peaks, may even change the angle of these things. You will be surprised when you use this that the topology optimization was indeed approximate. When you do these further iterations of optimization, the answer gets better and better. The other thing we've been doing is we want our product to become sort of a design system in and of itself, to be honest, because we want to take it as far as we can before you do the real detailed CAD work. So we've been going quite a ways with our polynurbs technology. So here we're showing that in addition to those very organic taffy-like surfaces you get from sub-Ds, we can put very sharp edges into those now. You can have flats, you can have perfect rounds, so we're doing filleting on the cage structure itself. So we have a really nice blended type of modeling approach that both captures the topology results and the intent that comes out of there, but also a lot of your own design intent or machine surfaces. So a very kind of mixed mode geometry approach. The other thing which is really cool about the cage structures that we're creating is that you don't have to realize them as just one way. So you saw these very smooth kind of taffy-like structures like you see on the top there, but we can realize them in more traditional forms as well. So rather than do that sort of sub-D type interpolation through it, we have other interpolation schemes we've developed, which are kind of our own. So in the middle one there, the user has declared he wants flats across the top and bottom surfaces and rounds across the middles. So maybe that thing is going to be machined, or maybe he wants radius corners and so forth. So you can go through that cage and you can define how you want this thing to be realized, and you can flip back and forth between these different approaches. Maybe you want it to be sheet metal, maybe you want it to be hollowed out, things like that. So it really gives you the ability to quickly generate many different design concepts for the same part. And we're working on other tools that let you Boolean these things together, so it just makes modeling with these things much easier. So let's talk a little bit about realizing these designs through more traditional CAD methods as well. So here's just a sample problem where we have this handle bracket, as it's called, and we have certain design criteria. We want to increase the stiffness from this original part. We have a certain frequency target we have to hit. And we want to understand whether it's better to cast this thing or to do an additive manufacturing process. So we get all the specifications from the people who are asking for this part. We have its material, things like that. That maroon is the design space. We set up the loads and boundary conditions. Hopefully we get them right. Kind of goes through the process we just spelled out, and we get the topology result on the right. So what you want to do once you get the topology results is you just do some quick studies right then and there on those results. Just get your displacements, get your basic frequencies. Those will change a little bit when you get more refined design, but you always want to get your baseline from what you just got out. So of course you do your standard FE, just integrate it right in the system to get it done. Then you can export that, and if you want, you can still export the STL, or you can do a polyNurbs and export it. Here we've exported it into SolidWorks. Onshape would be a good choice as well, or any of the others. And we get sort of a traditional kind of machine-looking part. You see the gray overlaid with the red right there. And you get a weight, and you get your final answer that from your traditional CAD approach. But again, in this case, we wanted to see if it would be better to do additive. If you're going to do additive, it probably makes sense to be more aggressive in the design and use a polyNurbs type approach. And there you see the very typical organic shape that comes out of there. So we've realized it in that form too. Because design is so iterative, there's lots of comparisons going on. We have this kind of multi-model environment, lets you bring multiple models, look at all your different iterations. We have pivot tables to let you rank between all the different attributes of your part. So the different performances that you care about, things like the stiffnesses and the first frequencies and the weights, all those things, you can just put them up in a nice table integrated at the bottom, just sort and rank their different designs as you go through them to compare. Because in practice, we found that people generate 10, 15, 20 designs in the course of a project, because these things can pop out pretty quick. And so it really gives you a nice playground. And just managing the ranking of all these different design decisions has become a big part of the process now. Okay, so now we're going to look at the two manufacturing alternatives. Well, if you're going to manufacture it in, say, a casting versus additive, then casting has its own issues you got to think about. The most common thing with castings is a guy hands a cast part design to the guy who's the casting specialist, and what goes wrong? You're going to have porosity issues. I don't like the amount of time it's going to take. I'm going to have too many risers on this thing because it's got a lot of material. It's going to cool slowly. Manufacturing is a critical part of the design process. Again, that's another reason why just popping out a topology answer based on loads is not the end of a design. So we have our click-to-cast product. We have a number of manufacturing solutions that we're building into our environment now. So here we did a casting feasibility of both designs, actually. So the one that was the more cast and machined looks like it'll cool in about 30 seconds using basic one-click sort of a simulation there in 57 seconds for the solidification on the more organic shape. So there's one advantage to think about. we've been spending a lot of time the last couple of years now integrating these manufacturing simulation technologies into our pipeline. So we have click to form and click to cast, do casting simulation, click to extrude. We can do metal sheet stamping type simulations. And we are putting those in two forms into the product. One is just straight into Inspire. We have a feasibility check. So it'll do really simple, quick checks for the designer to know if he's on the right track or not. And then we have a full formed product that does the full detailed simulation of each of these processes as well. But we wanted it built into the initial concept design software because it's so critical to understand the feasibility while you're doing concept design. So those are the three products so far, and certainly more to come. So just looking a little deeper at casting then, as I mentioned, the things you want to look at for feasibility of a design that's going to be cast are air entrapment. You don't want bubbles in your design. Porosity is a big issue. You get a lot of voids from porosity. And cold shuts, which means because it's filling the mold, it kind of solidifies too quickly and blocks a path, so you don't get a full fill. Those are the three most common problems, and they can be avoided right from the get-go if you just plan it and include that into the whole optimization loop in the concept. So we take it a step further as well. If you want to set up a part for doing casting simulation, even in the concept stages, we take some of those same tools that are in Inspire and we've just posed them for the guy who wants to do a quick, more detailed casting simulation. So first thing you do is you have to find out where you have plugs in your design. So here he just finds all the voids, it fills them for him. He can extend them a little further. He can indicate where he might want sprues and gates and things of that nature. Now our goal is once you run the casting simulation is it's going to find where you're going to have those porosity issues, which we just showed you a little earlier. It's going to automatically recommend where you need risers, by what volumes these risers can be. Not that you want to do a full, final, detailed simulation of the casting process. You can with this, but what you want to do even in the concept stage is understand that's actual material that you're using. Again, topology optimization gives you kind of just the part itself, but the real problem is what's the total cost of materials that go into making it, and how much scrap am I going to produce, things like that. That's what designers have to answer in real world every day. And so getting a quick thing where they can set up in a few minutes and get some real answers is quite important to them. And if you want to go further, you can even put in the cooling systems and things like that. So we go quite far into the manufacturing end of these things. And what we're finding is the concept designers love to go into this end of things to really get all the answers they need when they're doing their comparative studies. So that was a little bit on the casting side. We also are doing quite a lot of work with people that are doing additive manufacturing implementations of these designs as well. So here we see an example of lattice generation for additive. So you could just print the solid part. We have options to generate lattice structures. And our lattice structures are a little different from what you've seen. Everybody's kind of doing research in this right now. You don't see lattice really in full production that much yet. It's one of those areas everybody's interested, they want to do research on it. So we've seen the kind of regular cell pattern fills that people optimize the thicknesses. Here's one that uses a different approach. It uses more of a tetrahedral cell, and it actually does all the optimization on each of the individual beams within there. I think I have a close-up here. And it can be a mix of solid. We have different parameters that we're experimenting with to have at what point do you want it to transition from solid to lattice? Do you want it to be all lattice? Do you want just lattice on the interior? Things like that. So we definitely have thrown our hat in the ring and done quite a lot of research in this, more ongoing as well. There's kind of more of a close-up as well. We've worked with Materialize so that we can export these lattices with the minimal amount of data over to the Materialize software through Magics and stuff so you can get them printed. So we've done a number of different projects with them to print these things out. Another thing we've added into the topology generation end of things is an overhang angle constraint. If you're really dead set that you're going to print this part and you know what kind of machine you're going to have, one of the parameters of the setup is what's the overhang angle that it needs to respect to avoid like head crashes and where you need supports. So you can actually say, if I know I'm going to print it this direction, please minimize my, my overhang angle. And that can really change the shape of your part as well. And finally, we're putting now into the software the ability to generate supports. And we were originally, we were going to say, well, we'll leave all that support set up and the print set up to the other companies like Materialize and others. But we've had a number of requests, and we understand this quite clearly now, is that once you've created these supports, they're part of your design, just like those sprues and gates and risers were in the casting. You really need these as part of the design so you can see if it's printable. If you're going to make design changes to that part, you want all those supports to come along for the ride as well, so you don't have to regenerate them from scratch each time. We'll be able to regenerate them for you. So a lot of work going on in that area right now as well. So just wrapping it up real quickly, we've been working really the last 3-4 years really heavily in the additive manufacturing space, both in plastics, but primarily in metals, to be honest, because we tend to work more heavily in the production end of additive manufacturing. So a lot of practical knowledge coming. And just to close it out, I'd be remiss if I didn't say we also have put our products in the cloud now. So the Inspire, which is really the host of all the technology that I just showed you there today, is available as a desktop product, but also through the cloud. There's a beta version right now where you can go to Inspire Unlimited and uses the full features of the software, and it adds in some nice data management and galleries and things like that. So last 3 points, just to reiterate, those boundary conditions are a big, big deal to getting topology right. Topology optimization can be fire in the hands of people if they don't really use it carefully, but they'll learn. So, okay, thank you very much, and I'm going to wrap it up right there.